Hello, in this video we will look at one of the most important statistical tests that is applied on choice models. It's the t-test. So the objective of the t-test is to analyze the question that a parameter of the model, let's say theta, is equal to a given target value theta star. And actually we would like to see if the value that we obtain from estimation is actually significantly different from this value theta star. Basically, the null hypothesis is that the true value of the parameter is indeed theta star. And the fact that we have a different value from the estimation, so theta hat, is a result of the fact that we have drawn a sample from the population and that we have used inference. So this is purely inference errors. That's what we mean by significant. So now if H0 is true, meaning that the true value of theta is equal to theta star, what we can show is that the statistic that is represented here has a given distribution. So the statistic, the distribution of theta hat, the estimated value, is distributed as a normal distribution. And more specifically, theta hat minus theta star, which in average should be equal to 0 if theta star is the true value of the parameter, divided by sigma, which is the standard error of the estimates, is a normal distribution with mean 0 and variance 1. So it means that if H0 is true, so if the true value of the parameter is indeed theta star, 95% of the time when we draw a sample and we estimate the value of theta from sample, the value that we will obtain will be between minus 196 and 196. Which correspond to the quantiles of the normal distribution. Now, if we look at this logical relationship in the other direction, it means that if the statistic lies outside this range, so if we happen to calculate the statistic and its value is below minus 196 or above 196, well, in that case, we can actually safely reject the null hypothesis. We know that we will make a mistake 5% of the time, but this is what we are willing to accept as a margin of error. So this is the idea of the t-test. When the statistic lies outside the interval minus 196 and 196, we say, okay, maybe it's due because we have drawn a wrong sample or very specific sample. Maybe. It will happen only 5% of the time. But we believe more that it is due because of the fact that H0 is not correct. So we want to reject it. Okay, so the statistic that we calculate, theta hat minus theta star divided by sigma, the probability that it lies between minus 196 and 196 is equal to 95%, as we saw in the picture. And actually, 95% is 1 minus 5%. So 5% is the level at which we would like to apply the test. So now the decision that we apply in practice is that we consider rejecting H0 at the 5% level if the statistic in absolute value is larger or equal to 196. But remember, I use here 5% for the sake of the example, but in the context of specification testing, there is absolutely no problem to use higher value for the level, meaning lower value for the t-test. So why is it called a t-test? In theory, if theta hat is asymptotically normal, which is the case with maximum likelihood estimation, and if the variance is unknown, which is usually the case, we use the estimated variance and not the true one, then a t-test should be used with n degrees of freedom. But in practice, you can see that when n, the number of observations in the sample, is 30 or larger, then this t distribution, the so-called student t distribution, is well approximated by a normal distribution. So therefore, in practice, because we most of the time have more than 30 observations, we can use the normal distribution to apply these statistics. So even if it is called a t-test, it is applied with the normal distribution. Now, sometimes it's useful to represent the same information using a different value, which is called the p-value. So the p-value will basically convey exactly the same information as the t-test, but in a different format. What is the p-value? The p-value is the probability to get a t-statistic which is at least as large in absolute value as the one which has been reported, if the null hypothesis is correct. So if you calculate a t-statistics, you can actually derive the p-value using this formula. It's 2 times 1 minus the CDF of the normal distribution calculated at t. And now you can use the p-value exactly like you use the t-test. Now, in practice, you would reject the null hypothesis when the p-value is lower than the level you are targeting. So, typically 5%. So if p is lower than 5%, you would reject the null hypothesis. The t-test can be also used to compare two coefficients. In this case, the null hypothesis is that two coefficients are equal. I mean, this applies in particular when you are making the assumption that a variable is alternative specific, so you assign a different coefficient for the variables in different alternatives. But then you may want to test if it is reasonable or not. So you test if the two coefficients that you have put are actually equal in reality. So this is your null hypothesis. The idea of the t-test is exactly the same. You calculate a statistics. This statistic is given as the difference of the two coefficients divided by the square root of the variance of this difference. And you can apply the formula for the variance in order to obtain this calculation here. And this statistic, again, is distributed as a normal 0, 1 if the null hypothesis is true. So now I suggest that you practice a little bit with these t-statistics for estimating a parameter against a specific value, calculate the p-value, and also use the t-statistics to compare two coefficients, to check the hypothesis that two coefficients are equal.